The result is the additive increase, multiplicative decrease congestion control algorithm. The algorithm is distributed, meaning that all the senders can act independently, and we've just shown using the phase plots that it's both fair and efficient. To visualize this sending rate over time, the sender's sending rate looks roughly as shown. We call this the TCP sawtooth behavior, or simply the TCP sawtooth. TCP periodically probes for available bandwidth by increasing its rate using additive increase. When the sender reaches a saturation point by filling up a buffer in a router somewhere along the path, it will see a packet loss, at which point it will decrease its sending rate by half. You can thus see that a TCP sender sends at a sending rate shown by the dotted green line. That is halfway between the maximum window size at which the sender sends and half that rate which it backs off to when it sees a loss. You can see that between the lowest sending rate and the highest is Wm over 2 plus 1 round trips. Now, given that rate, we can compute the number of packets between periods of packet loss and compute the loss rate from this. The number of packets sent for every packet lost is the area of this triangle. So the loss rate is on the order of the square of the maximum window divided by some constant. Now the throughput is the average rate, 3/4 W max, divided by the RTT. Now if we want to relate the throughput to the loss rate, where we call the loss rate P and the throughput lambda, we simply need to solve for Wm, and I'm just going to get rid of the constant. So a loss occurs once for this number of packets, so the loss rate is simply 1 over that quantity. And then when we solve for Wm and plug in for throughput, we see that the throughput is inversely proportional to both the round trip time and the square root of the loss rate.